Good evening, sky people. Welcome back to the Astro-Imaging channel, our weekly YouTube show about all things astrophotography. Tonight we have with us Rod Pommier, who will be talking about a less imaged type of object, globular clusters, what they are and how best to image them. Next week, we're going to have Craig Stocks back with us to talk about how to simplify your image processing workflow and streamline some of the more tedious tasks related to image processing. In the following week, we're going to have Gary M. with us again. He's been imaging a whole bunch of VDB or Vandenberg nebula recently, which is a collection of certain types of stars surrounded by reflection nebula. And some of them he posts, I'm like, I don't see the nebula, but they're supposedly there. He's been very busy doing that. But before we get to Rod, a couple reminders. Remember to hit like and subscribe if you like what you see here. It helps us get our awesome content out to the masses. Also, this being a live show is a great opportunity for you, the live audience, to ask questions of our speaker. So just put questions in the chat and we'll ask them to the speaker, and then you can have your question answered live on the air. One of the benefits of coming to the live show instead of trying to catch it later in the week. Yeah, I think that's all the important stuff. So let me introduce Rod here. So he is a surgical oncologist and professor of surgery, has been doing astrophotography for 36 years. He's published a number of articles in Sky and Telescope and Astronomy magazine that are all illustrated with his own astrophotos. Pretty impressive background. So I'll turn it over to you, Rod.
Well, thanks, Molly, for the very warm introduction. And Terry, I'll take a confirmation that I'm showing up on your broadcast screen.
Yeah. Sorry, my mic was off. Yes, you're here.
Okay, great. Well, good evening, everyone. My name is Rod Pommier, and I'm in Portland, Oregon, and it's great to be back on this show. And tonight I'm going to be talking about glorious globulars. So in my mind, globular star clusters are among the most beautiful of deep sky objects. I mean, these dazzling spheres of typically hundreds of thousands of stars never fail to delight viewers. And you can certainly bet that show-stopping globular clusters like M13 in Hercules or Omega Centauri will be shown at star parties and observatory tours. However, once you get past M13 and Omega Centauri and maybe a short list of a few others, the trail of globular star clusters in the world of amateur astronomy quickly grows cold. Sadly, if you ask them, most amateur astronomers have observed only a handful of globular clusters. And this seems to spill right over into astrophotography because similarly, most astrophotographers have imaged only a few globulars. Go ahead and check out the website or Astrobin page of some astrophotographer you admire or emulate, and you'll find that their pages are replete with images of galaxies, nebulae, solar system objects, and sure, they'll have the obligatory image of M13 and or Omega Centauri, but you'll find that very few of those astrophotographers display a significant number of globulars. Now, when the sky is offering us so many globular star clusters that we could image, I have to ask, why is it that we image? Yeah.
We've lost your video and it was getting pretty choppy. You might consider turning off your video for the sake of your audio.
Okay.
What about leaving the stream and coming back in? Sorry, on Rod's end, the meeting and then coming back in. That may help. Is that possible?
Possible. I don't want to lose them longer than we need to.
Where are we now?
Why don't you just, we'll see how your screen sharing goes, but let's go ahead and press for the moment.
Molly's also breaking up a little. So it's not just, are we coming in from Australia tonight?
Yes.
Yeah. Everything is fluid on my end here.
Terry, you muted.
Sorry. Stuff is fluid on my end. Did you want to swap over to the secondary stream? And just
yeah, it's pretty choppy as I'm looking at it here as well.
Yeah, YouTube is very choppy.
Yeah.
Yeah, I'm dropping a lot of frames now. I can see that.
Okay.
There's nothing running in the back here. Let's verify stuff here.
Do you want to try and swap to Jaime?
Is that possible?
It would be the same on my end.
I can pick it up as well. I've got Streamlabs
Yeah.
open here.
Okay, so do I just end mine and then you
Not
can...
yet.
Okay.
Let me take it
Yeah.
over. Oh crap. Okay.
We
I'm
don't
not
want to lose the broadcast here.
Yeah, I'm actually not going to be able to take it. It looks like because you've already grabbed it. Flip. I don't know how to do that. Yeah, it's not showing this stream. Son of a gun.
Folks, this is what happens when we have live YouTube, and we actually have two streamers all the time when we're doing this. I'm going to be talking for a little bit so they can just do what they need to do. What we can sometimes do is grab the stream and switch it over to one of the other streamers. We're going to look into doing that right now. In the meantime, if you've got any general questions you want to ask over in chat, well, we'll try to answer them as well as we can. It's just the fact of life with live YouTube or live video, live shows of any kind, and we have to make some swapping around. One of the things we may need to do is send you off to a different stream. I don't know how we would do that. Just give you a different URL for the YouTube tonight. But we'll give it a few seconds for these guys to work out what they're doing. Give a few minutes for these guys to work out what they're doing, and we'll get back to it.
Alex, the voice is coming over pretty well, so maybe if Rod just turns off his video.
Yeah, let's go ahead and press for now, and I'll see what I can do on my end, because I like the old manual stream settings I used to have it on. So
okay, so this is Rod is turning off his video
yeah,
and
Yes,
continuing
it's just
his
Rod.
presentation, and we'll take it from there. Bear with us, folks.
yeah. Let's go ahead and press with Rod sharing a screen, not playing his video. Rod, are you still there?
Yes.
All right, why don't you go ahead and
I'm
share your
trying
screen.
to reboot the screen sharing here.
Okay.
Are you getting my show now?
Yes, we're getting it here. Let's see if it pops. I think it's going to pop up on YouTube in a moment.
We can see things before you guys can. There you go. You're on.
You're good.
All right. Do you want me to pick up where I left off?
Yes, please.
Okay, so as I was saying, sadly, most amateur astronomers have observed only a handful of globulars. And this seems to splash over into astrophotography because most astrophotographers have imaged only a few globulars. And if you check out the web pages of some prominent astrophotographers, you'll see they've got lots of images of galaxies, nebulae, solar system objects, and an obligatory image of M13 and/or Omega Centauri, but very few globular star clusters. So I have to ask why, when the sky is offering up so many of these glorious globulars that we could image, is it that we image so few of them? And I think this has to do with a really big negative misconception about globular star clusters. So let me explain that with a little story from my life. You see, I used to be one of those observatory tour guides. This is the University of Oregon's Pine Mountain Observatory under the dark skies of Central Oregon. And this is the dome that houses the 24-inch telescope. And so, as I said, I used to do film astrophotography in the 80s, 90s, and 2000s, and I did it right outside this dome. The University of Oregon would let me run as many extension cords as I wanted out of the power sockets to run my clock drive, my dew zapper, and other electrical equipment. They let me sleep in the astronomer's residence during the daytime, where I had a stove to cook hot meals and even a hot shower. But in exchange for those amenities, they wanted me to give tours to the tourists who showed up on summer weekend nights. So as it got to be dark, I would gather the tourists in the dome and seat them in folding chairs, and I would give them a talk about astronomy and some of the objects we'd see that night. And on the walls, we had black and white, very large posters of images from Mount Wilson Observatory of things like M13 and Hercules, the Whirlpool Galaxy in Canis Venatici, and the Pinwheel Galaxy in Triangulum. And I can tell you that the excitement and anticipation of those tourists as they gazed at those posters and looked up at the telescope towering above them was palpable. So I always started the show with M13. As I said, it's a showstopper and never fails to delight. And the oohs and the ahs and the oh my gods as people looked through the eyepiece for the first time and saw this just reverberated through the dome. And that's because that object looked like the picture on the wall. In fact, it looked better than the picture on the wall, because if you look at this picture, the central core of the globule is just all burned out and overexposed. But when they looked through the eye, they could see countless resolved stars right down to the core. The other deep sky objects were a big disappointment. When people looked at the Whirlpool galaxy, well, first of all, it's really tiny. I mean, any of us that have tried to image it have found it's nowhere as near as large as we're led to believe when we see pictures like this. So when they looked through the eyepiece, they could see the core of M51 and the core of the galaxy that's a companion NGC 5195 and one spiral arm coming out, but nobody ever saw the spiral arm that connected the two galaxies. It's just too faint. So people would look at the eyepiece and say, that's it? And they'd say, yep, that's it. It was even more disappointing with M33 because it's so large, so diffuse, and so faint. So people look in the eyepiece and say, where is it? I don't see anything. And I'd say, well, actually, it's filling nearly the entire eyepiece. And they'd look again and say, oh, is it the fuzzy thing in the center? And it's like, no, that's just the core of the galaxy. Now, if you use the averted vision I talked about, you'll see a big oval around that that's just barely brighter than the background sky. And so suffice it to say, the disappointment that people when they saw these faint fuzzies knew no bounds. So before I had a riot on my hands from disappointed tourists, I would quickly revert back to globular clusters. And there were plenty of them. I could go to M3 in Boötes and drop down to M5 in Serpens Caput and pick up M10 and M12 in Ophiuchus, down to M4 in Scorpius, over to M22 in Sagittarius. And oh, look, M15 is rising in Pegasus. But there was almost always a group of jaded, and I mean jaded, amateur astronomers in the tour group. And I get it, they drove hours across the Oregon desert because they wanted to see the faint fuzzies through the 24-inch telescope and perhaps get better views than they had through their backyard telescopes back in light-polluted cities. So it wasn't very long before one of them would yell at me and say, stop showing us globular clusters. And then came the words that just wounded my heart. If you've seen one globular cluster, you've seen them all. I can't tell you how many times I've heard that, and I've heard it at star parties also. And of course, the implication from that for us astro-imagers is if you've imaged one globular cluster, then you've imaged them all. So there's very little reason to go beyond M13 and Omega Centauri. Well, I'm here tonight to tell you that that simply is not true. While I will concede that globular clusters may not exhibit the infinite variations of size, shape, and arrangement found among other deep sky objects, they still exhibit considerable diversity if you know which globulars to image, what to feature in those images, and how to effectively process them to bring those features out. For example, did you even know that there are 12 different classes of globular star clusters? Well, there are, and we'll go over that later on. But to think about it, if you just dedicated yourself to image half of them as an example, that would keep you occupied for quite a while and probably greatly increase the number of globular clusters you have in your astrophotography portfolio. So in the past 10 or 11 years or so, I've actually had 13 of my images of globular clusters published in Astronomy magazine. And I'm pretty sure I did that by showing what was different about each star cluster. I can assure you the magazine has no interest in publishing an image that looks just like the last one I sent them. So here's what I promised you for tonight. First, we're going to learn about globular clusters and get excited about them. Learn about their tremendous significance to astronomy and cosmology, perhaps some things you never thought about, like the search for extraterrestrial intelligence and world literature, and why they make great astro-imaging targets. After a break for questions, I'm going to talk about how to make your globular cluster images distinct from one another so they don't all look the same. And then after another break for questions, I'm going to give a real-time image processing demonstration of a globular cluster using some tips and techniques that I've developed that are very straightforward, a series of about 5 or 6 steps that are guaranteed to give you good results so you can get globular clusters looking sharp right out of the gate. So let's get excited about globular star clusters. So why image globulars? Well, as I already said, they're beautiful, but let's not forget they're colorful. Globular star clusters shouldn't look like a splotch of spray paint on black velvet. They contain red giants and blue stragglers that make them colorful as well. They have large apparent sizes. Many globular star clusters are a substantial, I repeat, substantial fraction of the size of the full moon. And that means you can image them with various systems. So if you have a short focal length system, you can capture the globular cluster in the context of its wide field in the sky. On the other hand, if you have a long focal length system, you can zoom in for high resolution details within the globular star cluster. They're bright. And that means you can get by with much shorter exposure times than you need for faint nebulae and galaxies and narrowband work where you need hours and hours and hours of sulfur-2 and oxygen-3. And that also means you can image them and get good results when the moon is bright. And I think one thing that's important to all of us that live in the cities is that you can image them from within light polluted cities because they're bright. And you don't need expensive narrowband filters. LRGB or one-shot color will do, with perhaps one exception that I'll show later. So what are globular star clusters? Well, they are a very large spherical conglomerations of many, many stars that are tightly bound by gravity, which makes them very stable. It would actually be very difficult to gravitationally disrupt a globular star cluster. They orbit the Milky Way in elliptical orbits within a spherical halo that is surrounding its disk. And that means generally their distances are going to be tens of thousands of light years from Earth. A characteristic of globular star clusters is that the stars are generally concentrated towards the center of the cluster, and that you will see is the basis of the classification system that we will discuss. But it really means that there are incredible densities of stars in the cores of globular star clusters. For example, if you took a 10 cubic light year volume around the sun, it would contain but 5 stars: the sun, 3 stars in the Alpha Centauri system, and Sirius. The same volume within a globular star cluster will contain at least 400 stars, and in the centers of some of the most dense clusters, at least 1,000. Another way to look at this is photometrically. So this is M2 in Aquarius, which is one of the largest and densest globular star clusters known. So photometrically, a 1 by 1 arc minute area in the center of this cluster puts out a whopping 37% of its total light output. An equal area just a couple arc minutes off the center puts out a mere 0.02% of the total light. So that tells you how densely concentrated they can be at the core. Within the cores, stars are only light days, not light years apart. And that means if you lived on a planet around a star in a globular cluster, the skies would be perpetually bright. How bright? Well, about as bright as 20 full moons in our sky. So this is actually the topic of a very famous novel written by Isaac Asimov in 1941 called Nightfall. And science fiction writers and critics claim this is one of the best science fiction stories ever written. So in this story, there's a civilization that lives on a planet with 6 suns, at least one of which is always up, which means it's never dark there. There's the aliens that live on this planet have no concept of nighttime or dark. The only time they experience dark is if they were to go into a cave or a room with no windows. And they're actually kind of afraid of the dark. And because their sky is always bright blue, lit up by at least one sun, they believe that they are alone in the universe. Now, they do have solar astronomers who are tracking the motions of these stars, and by tidal effects, they detect that there's a dark moon in the system. And they are predicting that it will produce an eclipse when there's only one sun in the sky, and that occurs every 2,049 years. So when that eclipse occurs, they are shocked because 30,000 bright stars appear in the sky. And of course, the implication of that is that this civilization lives within a globular star cluster. So I'm not going to give you any spoilers to see what happens when this civilization finds out they're not alone in the universe, but I definitely recommend you read this if you have not, because it's a great read. So how many globular star clusters are there? Well, we believe that all major galaxies do have globular star clusters. And globulars are believed to form from the leftover gas in a galaxy's halo early on in the formation of the galaxy. And we now have very good proof of this from the James Webb Space Telescope. On the left is a frame of some of the most primitive distant galaxies that the James Webb Space Telescope has yet imaged. And on the right, we have close-ups of Galaxy 1, this zone 2 over here on the right, and Galaxy 3 down here. And if you look at these images, you can see these little golden blobs in halos around all these galaxies, and those are globular star clusters. So they're there from the very beginning of the formation of galaxies. The Milky Way has 157 known globulars. Now we believe there are many, many more that we cannot see because the Milky Way itself blocks out our view of them. 29 of these are Messier objects, and although they're spewed from M2 all the way up to M107, notably 12 of the first 24 objects in the catalog, a full 50%, are globular star clusters. Now, there are globular clusters in other Messier galaxies. For example, M33, the pinwheel galaxy in Triangulum, is known to have 122 globulars. And if you have imaged the M33 before, you may have imaged some of these globular star clusters without even knowing it. I have. This is an image of M33 I got published in the November 2014 issue of Astronomy. And it turns out that I actually captured 11 of M33's galaxies in this image. I've probably captured more, but I don't have any way to identify them. M31 Andromeda has 400 globulars. And again, if you've taken pictures of M33, you may have imaged some of them without knowing it. This is an image that I got published in the December 2017 issue of Astronomy, and the subject was the giant star cluster NGC 206 in the Andromeda galaxy, which is about 4,000 light years in length. But it turns out I also imaged about 18 of M31's globular star clusters, nearly as many as we have in the Messier catalog. Hopefully here's a picture you recognize from my talk I gave in August of 2022 about using astrophotography to measure the distance of the Andromeda galaxy using this Cepheid variable marked with tick marks. And I use this as the title image of the article I published along that topic in the August 2022 issue. But it turns out that I captured 35 of M31's globular star clusters in this image, which is more than we have in the Messier catalog. So you can image globular star clusters at images of about 2.5 to 2.7 million light years. Other galaxies in the Messier catalog have thousands of globular clusters. This is M104, the Sombrero galaxy in Virgo, and it lies 29 million light years from Earth, and it is known to have approximately 2,000 globulars. So this is an image I shot of it, and it's not a very deep exposure because it only appears between a couple of trees for a short period of time from my house. But when I zoomed in on it, it turns out that using the Hubble catalog, I can find out that I imaged 7 of its globular star clusters. So I'm now imaging globular star clusters at a distance of 29 million light years. The record holder for globular clusters is M87 in Virgo, which lies at a distance of 53 million light years. And it is known to have 15,000 globular star clusters. So this is a wide field image of M87 and some of its surrounding friends of galaxies. But if we zoom in on this M87 in this image, besides seeing the relativistic jet from the supermassive black hole, I've counted over 150 globular clusters buzzing around this galaxy. So now I'm imaging globular clusters from a distance of 53 million light years. But I think another reason to want to image globular clusters is because of their tremendous cosmological significance to astronomy and cosmology. For one, they helped us determine our location in the universe. This is Harlow Shapley, who was director of the Mount Wilson Observatory in the early years of the 20th century. And he used the 60-inch reflector atop Mount Wilson to measure the distances to as many globular clusters as he could. And what he found was that they were contained within a spherical distribution around the plane of the Milky Way. And he found that there were many in the direction of Sagittarius, Scorpius, and Capricornus, and some of them were at moderate distance and some were at tremendous distances. But looking in the opposite direction towards Taurus, Orion, Lepus, and Canis Major, he found only 3, including this one, which is M79 in Lepus. This is one of the rare wintertime globular clusters, but it's always held a special place in my heart because of what a tremendous role it played in determining our position in the galaxy. So what Shapley did is he correctly assumed that the center of this spherical distribution of globular clusters was also the center of the Milky Way. And that meant that this distribution of globular clusters told us we were not at the center of the galaxy as had previously been assumed, but we were located about halfway out from the center of the galaxy to the edge of the disk, giving us our biggest demotion of position in the universe since Copernicus put the sun at the center of the solar system. Globular star clusters have also been extremely important in determining the age of the universe. So how do you determine the age of a star cluster? Well, first you assume that all the stars were born from the same nebula at roughly the same time. And then if you plot the stars on a Hertzsprung-Russell diagram, where you plot their temperature or their spectral class along the x-axis going from bright to dim, and their absolute magnitude going from dim to bright along the y-axis, you'll find that the vast majority of stars follow along this squiggly line known as the main sequence. This is where stars plot when they are fusing hydrogen and hydrogen into helium, which is what they do for a lot of their lifetime. But when they run out of hydrogen, they collapse, and when the core pressure gets high enough, they will fuse helium and helium into carbon, and they will expand and cool and turn into red giants. And what we see in the Hertzsprung-Russell diagram is that they move directly to the right and make a horizontal branch. Now, this horizontal branch comes off of the main sequence directly from the stars which generated them. So the rest is just physics. If you go up here to O blue supergiants, these are huge stars that live fast and die young. They'll run out of hydrogen and have to fuse helium within a few million years. So if you see a horizontal branch here, the star cluster is only a couple million years old. If you go down to a class A star like Vega, they have enough hydrogen to last about 1 billion years. So if the horizontal branch is coming off here, as we see in this diagram, the star cluster is about 1 billion years old. The sun is a class G star, and we know it has enough hydrogen to last for about 9 billion years before it turns into a red giant. So if you saw a horizontal branch here, it would tell you that the cluster is about 9 billion years old. Well, if you plot a Hertzsprung-Russell diagram on a globular star cluster, they have a horizontal branch. It's short and it's way down here, which tells us that the age of globular star clusters is about 12 to 13 billion years old. So it turns out that globular star clusters are actually the oldest objects in the sky that you can photograph. Now, this caused a tremendous paradox when Hubble discovered that the universe was expanding. This is a famous graph from his paper on the expansion of the universe. On the x-axis, he plotted the distances to galaxies that he determined from various techniques, and along the y-axis, he plotted its velocity of recession from Earth based on its redshift. And what he got was this very nice linear relationship that is known as Hubble's law. And the slope of that line is known as the Hubble constant. It tells you the speed at which the universe is expanding. And that turned out to be 250 kilometers per second per megaparsec. Now, the cool thing you can do with this is you can basically run this line backwards and find out when were all the galaxies together at the beginning of the universe, or the Big Bang. And if you use this value of the Hubble constant, it gave an age of the universe of 4 billion years. So that created a tremendous paradox. How can globular clusters at 12 to 13 billion years be older than the universe at 4 billion years? So astronomers came up with very clever ways to try to explain this. This is a graph from a very old astronomy paper, and what it shows is time along the x-axis and the size of the universe along the y-axis. So at time zero, we had a big bang, and the universe began expanding, but it slowed down due to gravity. And at about 4 billion years, we had this point in time where the slope of the Hubble constant would have been the required 250 kilometers per second per megaparsec. But then astronomers imagined that the gravity continued to slow down the expansion of the universe, and it went into this prolonged loitering phase where it barely expanded. And then they posited that there might be some unseen force that caused the universe to begin expanding. This was almost prescient about the concept of dark energy, which hadn't been discovered yet. And so they basically said the universe would begin expanding, going toward a runaway expansion, which means there would be another time on this curve where the Hubble constant would equal 250 kilometers per second. And they can arbitrarily say that happens anytime they want. So they just conveniently said, how about if it's now, when the universe is 13 billion years old, and now we can have a universe that is old enough to harbor 13 billion year old globular clusters. Of course, this all turned out to be wrong because Hubble's estimate of the Hubble constant was wrong. We've since come up with a much better standard candle to measure the distances to galaxies, and those are type 1a supernovae. So on this graph, we have much greater distances out and much longer redshifts. And all of Hubble's data on that first graph I showed you fits in this little red box. So you can see how a little tilting of the slope a little this way or that way would throw you way off. So these data that we have in modern times give us a Hubble constant of only 73 kilometers per second per megaparsec. And that gives us an age of the universe of 13.4 billion years, which is older just barely than the globular clusters. You may not know it, but globular clusters have played a very important role in the search for extraterrestrial intelligence. This is Frank Drake. He's an astronomer who died about 2 years ago, but he was the founder of SETI. And he's famous for starting the OSMA project at the National Radio Astronomy Observatory in Green Bank, West Virginia in 1960, listening to nearby stars like Epsilon Eridani to see if he could pick up signals from an intelligent civilization. He's much more famous for publishing the Drake equation 2 years later in 1962. The Drake equation is an estimate of the number of intelligent civilizations that exist in our galaxy, and that is the number n. And it's equal to R star, which is the rate of star formation, times the fraction of stars that have planets around them, times the number of planets that have are stars that have planets in the Goldilocks zone where you can have liquid water, times the fraction that develop life, times the fraction that progress to intelligent life, times the fraction that proceed to have a civilization, times the length of time the civilization exists before it's wiped out or destroys itself. Now, as brilliant as this equation is, it can be manipulated in different ways. Some people throw in very liberal values for all these variables, and they come up with literally thousands or trillions or millions of intelligent civilizations in the galaxy. On the other hand, people can throw in very conservative values and make the number of n come out to be just 1, which is us. So the problem is we really don't know the numbers for very many of these things. The Kepler Space Telescope has helped because now, besides knowing the rate of star formation in our galaxy, we have an idea of what fraction of stars have planets and what number of them are actually in the Goldilocks zone. So we may make progress on this. But Frank Drake is much more famous for the Arecibo message. This was broadcast from the Arecibo radio telescope in Puerto Rico when he was there. And so this is the Arecibo radio telescope, which recently collapsed. And one of the first things Frank Drake did when he got there was calculate that if it was a cereal bowl, it would hold 350 million boxes of cornflakes. But the important event occurred on November 16th, 1974, when he broadcast a message with an energy of 30 trillion watts, which made Earth the brightest radio source in the universe for about 3 minutes. The message he broadcast was binary. It was 1,817 bits at a rate of 10 bits per second, so it took a little over 3 minutes to broadcast. The message was binary. It had a carrier frequency of 2,380 megahertz, which if you want to think in binary, it could be a 0. And then he modulated it at various times up to 2,390 megahertz, which in binary you can imagine as a 1. Now, 1,817 is what you call a super prime number, because it's the product of two other prime numbers, 23 and 79. So this message is a brilliant exercise in how you could communicate with an alien civilization if the only things you had in common with them were mathematics and chemistry. So if you arrange this message and you imagine that a 0 is a dark pixel and a 1 is a light pixel, and you array it out in a 23 by 79 grid, you get this message. So in the top, it's binary, counting 1 to 10. And then it goes to chemistry. These are the numbers in the periodic table of the elements of life: hydrogen, carbon, oxygen, nitrogen, and phosphorus. And then come the empiric formulas of DNA. So this is deoxyribose and phosphorus on the left and right sides. And in between, we have the empiric formulas for adenine, thymine, cytosine, and guanine. And he paired them just like they are in DNA. Down here is a representation of a double helix of DNA. And in the middle is 400,000 in binary, which is the number of base pairs they believed was in the human genome. Then comes a stick figure of a human being with an indication of how tall we are. And here's a blue bar showing that what we're representing here is our height. And here is 5 billion in binary, telling us how many humans were on the planet at the time of the broadcast. Here's a model of the solar system with the sun, and they still counted Pluto as a 9th planet. And the 3rd planet, or Earth, is set out from the others to say where this message came from. And lastly is a representation of the Arecibo radio telescope, again with a blue span and an indication of how big that dish was in length. So the question is, where would he send this message? He got to send it once. And where he decided to send it was to M13 in Hercules, because it contains hundreds of thousands of stars, each of which might have many, many planets. So it was the best way to capture as many civilizations as possible in a single broadcast. So it will take 25,000 years for the message to get there. If anybody responds, it'll be 25,000 years till we get the response. I have one artifact in my astronomy collection from Frank Drake, and this is one of Frank Drake's wine glasses. And on it, it has the Drake equation etched in paint. So that's a whirlwind tour through globular star clusters. Do we have any questions at this time about them?
I don't see any questions. If someone else can take a look. I see when you showed M13, you showed the little propeller structure.
We'll get to that shortly, Eric.
Oh, I love that propeller. I mean, there aren't many, secondary structures in these things, but if you can get that, you can get a decent image. Lots of chatter, but I don't see any questions.
All right, we'll go forward to the next section. So the next section is about making globular images distinct from one another so they don't all look the same. So there are a number of ways we can do this. One is by emphasizing their Shapley-Sawyer class. We can then focus on features within the globular star cluster itself. We can focus on foreground objects in front of the globular star cluster, background objects behind them. And then if you post paragraphs about your images, you can also list interesting facts about the globular cluster. So let's begin by discussing the Shapley-Sawyer classes of globular star clusters. So back to Harlow Shapley, while he was working on globular clusters, he paired work with Helen Sawyer, who later became Helen Sawyer Hogg when she got married in 1930. And they developed a system of globular star clusters. Helen Sawyer Hogg's one of my favorite astronomers. This is a book that she published in 1976, and this is my copy. And it's a delightful book on how to enjoy astronomy, so I highly recommend it. So they worked on the Shapley-Sawyer classification system between 1927 and 1929, and it divides all globular clusters into 12 different Roman numerals, 1 through 12. I published an article that describes this in great detail in the August 2014 issue of Astronomy, but I'm going to give you the Reader's Digest version here to make it simple. When you look at classes 1 through 4, they all have dense, essentially unresolvable cores. When we move from classes 5 through 8, the cores become resolvable, and this produces the common snowball of stars effect that we see in globulars like M13 and Omega Centauri. Then when we get up into the higher classes, 9 through 12, the cores appear to break apart, and we can actually see gaps between the stars. So many gaps that if you felt like you had an eternity of time, you could actually count every single star in the cluster. Another factor that goes along with this is that generally, as we go from class 1 up to class 12, there's an increase in what I call the beehive effect, which is the number of scattered stars in the periphery of the globular star cluster. So if we look at the Messier catalog, we actually have an example of every single class of Shapley-Sawyer globular cluster in the catalog except class 12. And you can see here that class 5 is the most common, but there's at least one of every type of class except class 12. This is a list of what would be the archetypal globular clusters for each class. Now, I'm not going to go through and show you all these classes one after the other because many of these globular clusters listed here as archetypes I'm going to show as examples of other things, so it get quite repetitive. But from now on, when I show a globular star cluster, beneath its name, I'll have the Shapley-Sawyer class so that you can see what that is. So let's move on to features within the globular star cluster. And Eric's already mentioned one of the most important, and those are the dark lanes in M13 and Hercules. This is a drawing done in approximately 1850 by Irish astronomer Bindon Stoney using William Parsons' 72-inch Leviathan telescope at Birr Castle in Ireland. And what he noticed was this Y-shaped dark lanes inside the core of the globular star cluster. Now, the modern name of this, as Eric mentioned, is the propeller because it looks like 3 blades of a propeller. So this is my image of M13 and Hercules. It is a class 5 globular, so we're into the effect of snowball of stars. And I sent this image into Michael Bakich at Astronomy magazine, and I said, Michael, I know everybody on Earth that's an astrophotographer sends you their image of M13. So my chances of getting an image of M13 published are probably equivalent to those of a snowball in hell. But this seems to show the propeller quite nicely, so I thought I'd send it to you anyway. And he quickly wrote back and he said, Rod, you're absolutely right. Your chances of getting M13 published are equivalent to a snowball in hell. But he said, I just pulled dozens and dozens of images of M13 that have been submitted over the years, many by astrophotographers I'm sure you know, and you're right. None of them show the propeller as beautifully as yours does. So he said he did publish it in the November 2018 issue of Astronomy because of the emphasis that I had of the propeller in this image. And then a little over a year later, Stephen James O'Meara, who writes a monthly article in Astronomy magazine, wrote an article on the propeller. And they used my image a second time because it shows the propeller well. Now, what the propeller is hotly debated. Some people think that these are just gaps in the globular star cluster where there are fewer stars, and other people think it's dark material. It is not something between us and the globular star cluster that is basically eclipsing it, because you can see stars in the globular cluster that are in front of this dark material. However, regardless of that debate, the fact that there is actually obscuring nebulosity in globular star clusters has been known for many decades. These are 2 of the classic papers that describe this dark obscuring nebulosity in globular star clusters. And you can actually photograph these things in a lot of different globular star clusters. So this is M2 in Aquarius. This is a class 2 globular. As I said, it's one of the largest and densest globulars known, hence class 2. But if you look at the periphery of this, where I said earlier, there's very little light output, down at the very bottom near the 6 o'clock position, you can see some dark, obscuring, curving, and arcing things. And it actually makes a bit of an X shape. So this got published in the August 2024 issue of Astronomy. This is M92 in Hercules, and I say too bad because everybody looks at M13 in Hercules, and few people bother to shift their telescope a short distance to gaze upon M92. It's a class 4 globular cluster, so it's just barely holding on to this dense, unresolvable core here. But what I want to point out is this object off to the left, or right at the 3 o'clock position. And if we zoom in, I thought that looked like a question mark without a period. So I dubbed this the question mark nebula within M92. And that got this published in the March 2019 issue of Astronomy. This is M3 in Canis Venatici. It's a class 6 globular star cluster, probably the second most famous northern globular cluster after M13. What I think is really fascinating about this is a squiggly line that goes all the way across the globular star cluster, almost as though it was a cracked egg. So if you look right here, you can see this squiggly line going all the way across the globular, consisting of dark, obscuring material. Perhaps the dirtiest globular star cluster in the sky is M12 in Ophiuchus. It's class 9, and it's just riddled with dark material that's blocking out stars behind it. Moving on to other types of objects in globular clusters, this is an image of M15 in Pegasus. It's a class 4 globular star cluster. This was published in the July 2020 issue of Astronomy magazine. And I want to point out this blue spot here. This is not another blue supergiant in the cluster. Rather, this is Peas 1, which is a planetary nebula in the globular cluster. Astronomers have studied this, and the redshift in the emissions from the planetary nebula precisely match the redshift of the globular cluster itself. So it's not something between us and the globular, it's actually in the globular. So this is the one instance in which I used narrowband. I got some oxygen 3 data, and I mapped that to the teal color and then added it to the LRGB image of the globular cluster. So here you can image a planetary nebula within a globular cluster. So we can also focus on foreground objects to make our images of globular clusters distinct. Most of the time when we're looking at a globular star cluster, it is away from the plane of the Milky Way, like M5 in Serpens Caput, which is a class 5 globular cluster, which means the star field surrounding it is fairly sparsely populated. But this is M56 in Lyra. Also too bad because everybody looks at M57 in Lyra, and few people shift their telescope a short distance towards Albireo to gaze upon this gem. It's a class 10 globular, and it's one of the smallest globular star clusters in the Messier catalog, even though it's lying at a fairly close distance of 33,000 light years. But to look at this globular star cluster embedded in this deep, rich field of countless colorful Milky Way stars is a real treat. And this was published in the August 2024 issue of Astronomy. This is M22 in Sagittarius, and it's a class 7 globular star cluster. And again, one of the largest apparent diameters of a globular star cluster in the sky. And this one is embedded smack dab in the middle of the summer Milky Way. So again, it's surrounded by countless numbers of stars, but look at how much fainter these stars are because there's so much intervening galactic dust. And if you actually correctly color calibrate this image and get the color balance right, this globular cluster doesn't look white, it will look yellow because so much of the light is scattered by the dust that's intervening, giving it a yellow cast. And even the blue giants in this have a lot of their blue light scattered by the dust. They are much paler than the foreground blue Milky Way stars because of all that intervening dust. So this is another globular star cluster that has a rich field of Milky Way stars around it. However, when it comes to a rich field of Milky Way stars, the Oscar certainly goes to M71 in Sagitta. This is a class 11 globular star cluster. You can now see how there is no dense unresolvable core. We've got lots of gaps in between the stars. For 2 centuries, people believed that M71 was just an open star cluster in the Milky Way. But in recent years, they plotted a Hertzsprung-Russell diagram of the members of this cluster and found that it has that short horizontal branch way down there on the Hertzsprung-Russell diagram, proving beyond doubt that it is actually a globular star cluster. And then we can emphasize background objects. Here's back to M13 in Hercules. The hawk-eyed among you may have noticed this galaxy, which is IC 4617. So this can give an image an incredible depth of field. M13 lies at a distance of 25,000 light years. IC 4617 is lying at a distance of 550 million light years in the background. Now, this is a fairly narrow field of view with my telescope, but a lot of you will know that up in this direction is another somewhat larger spiral galaxy, which is NGC 6207, and that lies at a distance of 30 million light years. But once again, it produces an incredible depth of field for the observer. Going back to M92 in Hercules, again, the hawk-eyed among you may have noticed this galaxy in the background, which is MCG7 3558, and it lies at a distance of about 400 million light years. So a lot of these globular star clusters are in regions of the sky away from the Milky Way, where we know there's going to be a rich background of very distant galaxies that you can capture in the image. And then I mentioned we can sometimes talk about interesting facts about the globular star cluster. So here's a map of our galaxy, and the arrow shows where we're located. And most of the time, we are confined to imaging things that are very, very close to us. We can't see all the things that are out in the rest of the galaxy, but surely, considering the beautiful objects that are near us, the galaxy must be hiding countless other objects that would be fun to image. So you ever, like me, wished you could image something that's in another distant part of the galaxy? Well, there is one way you can, and that is with M75 in Sagittarius. This is the only class 1 globular star cluster in the Messier catalog, and it is lying at a distance of 63,000 light years. So what is happening when you view M75 is we're located here in the Orion spur of the galaxy. And when you look at M75, you're gazing past the south side of the galactic core and visualizing a globular star cluster that is hovering above the outskirts of the far side of our galaxy. So this image got published in the August 2024 issue of Astronomy. And then there's the new field of galactic archaeology, and globular star clusters are playing a tremendous role in this. So the Gaia Space Telescope was launched by the European Space Agency in 2013 to do astrometry. And its task was to map 2 billion stars. It got the distances of the stars by parallax, by measuring the shift in the position of the star from the same position in its orbit around the sun 6 months apart. Then after 5 years, it imaged each star from the same position in its orbit and measured its proper motion, how far that star actually is moving. It has 2 spectrographs on board, one that picks up the chemical signature of the star and tells what elements are in it and in what proportions. And then there's a radial spectrometer that is measuring the red shift or blue shift of the star and picking up whether or not it's coming toward us or moving away from us and at what velocity. And if you take the proper motion and the shift, that gives you its 3-dimensional velocity vector in space, how that star is actually moving. Now, what this has done is it's identified many families of stars that have identical or very similar chemical structures, which means they were born out of the same nebula or material. And a lot of these families of stars are found to be in star streams, literally rivers of stars flowing in and around the Milky Way. So once you have these families, they put all this data into the eMosaic supercomputer with a neural network. And MOSAIC stands for Modeling of Star Cluster Formation in Cosmological Simulations. And they basically ran the clock backwards in time to see how our galaxy formed. And so this produced a series of papers in 2020 within the monthly notices of the Royal Astronomical Society. And the cool thing I got to do is I actually read these papers for my research in the Royal Astronomical Society library. And that portrait is of Francis Baily, who was president of the Royal Astronomical Society for a lot of years. He of the Baily's beads during eclipses. So what these papers showed was that the Milky Way has been built out of 5 mergers with other dwarf galaxies throughout the history. The first one occurred about 11 billion years ago when a much smaller, formless, barely rotating diskless Milky Way collided with a galaxy that has been named Kraken. And that added about 10% of the stars to the Milky Way and gave us our first primordial disk. The next major merger occurred with a galaxy that's been dubbed Gaia Solidus. This occurred about 9 billion years ago. It added another 10% of the stars to the Milky Way and gave us the thick disk that the Milky Way has now. Virtually all of the stars in the current disk of the Milky Way can be attributed to this collision, either as imported stars or stars formed out of the mixing of Gaia Enceladus hydrogen with Milky Way hydrogen. And the last major merger that I want to talk about is with the Sagittarius dwarf elliptical galaxy. That began 7 billion years ago, but this merger is not yet complete. So the Gaia Enceladus merger completely changed our concept of globular star clusters. Historically, we have believed that all of the Milky Way's globular clusters were formed out of leftover gas in the nascent Milky Way's outer halo. But what the eMosaic simulations have shown is that when Gaia Enceladus merged with the Milky Way, it brought some of its own globular star clusters with it that survived the merger and now orbit our galaxy. And those include M2 in Aquarius, M56 in Lyra, M79 in Lepus, and M75 in Sagittarius. So some of the interesting facts that you can talk about this is that M75, unlike the other globulars over the Milky Way, is in an extremely elliptical orbit around the Milky Way, which is a clear indication of its extragalactic origin. Even stranger is M56. It orbits in a retrograde orbit around the Milky Way in a completely opposite direction from all of the other globular clusters and the direction of rotation of the Milky Way, which is again a very strong proof of its extragalactic origin. Much of the Milky Way's current morphology as a barred spiral galaxy is directly attributed to our collision with the Sagittarius dwarf elliptical galaxy, which started 7 billion years ago. And as I said, this merger is not yet complete. So this is the artwork done by Roan Kelly for my article about this in the August 2024 issue of Astronomy, and she kindly let me use it for tonight's presentation. So what Gaia found is, or arcing high above and below the poles of our galaxy, are the Sagittarius star streams. These are not original Milky Way stars. Rather, they belong to the Sagittarius dwarf elliptical galaxy. And if you look at this map of the Milky Way, you can see what's left of most of the galaxy besides those streams, just south of the galactic pole or center in Sagittarius. And if you look at the very, very center of that ellipse, what you will find is globular star cluster, quote unquote, M54 in Sagittarius, which is a class 3 globular lying at the enormous distance of 73,000 light years. Now, it doesn't look like much. If I go back and look at my Messier marathon notes from the 90s, I wrote down perhaps the most boring object in the Messier catalog. But what we now know is that this is not a globular cluster at all. It's been masquerading as one for 2 centuries. But in 1994, data showed it was not of the Milky Way galaxy at all, but it is really the surviving core of the Sagittarius dwarf elliptical galaxy, and Gaia data robustly confirm that. So the Sagittarius dwarf elliptical galaxy's first encounter with the Milky Way triggered an enormous burst of star formation in the Milky Way galaxy that included the spiral arm that contains our sun, which means that first collision of the Sagittarius dwarf with the Milky Way galaxy triggered the formation of the sun, the Earth, life on Earth, and even us. So I no longer look at M54 with disdain as perhaps the most boring object in the Messier catalog. Rather, I think it's an object to be sought out, imaged, and even revered because we owe our very existence to it. And so if you want to read more about these mergers and acquisitions of these alien globular star clusters, this is all written up in the August 2024 issue of Astronomy magazine. So now we can take a second break and see if we have any further questions.
Yes, a couple questions, Rod. So John asks, are there any star forming regions in these globs?
No, they seem to be completely quiescent now and not forming stars any longer, except the stars do transform. They go into from main sequence stars to red giants and blue stragglers. They evolve.
So the parallel question is, are there supernovae? And I guess the answer would be yes, since you showed at least one planetary.
Yeah, we haven't seen one. I don't think one has ever been recorded in a globular.
Considering the density of the stars in that
They
seems
certainly must be in there occurring, yes.
Yeah, that seems kind of odd.
The other question is, do they have black holes? And so M15.
That was my third question.
And another globular, NGC 6 something something something, are known to have black holes. And it's presumed that perhaps all of them do, but we only have proof at this point for 2 of them.
And Alex asks, is there any motion? Do they rotate around some kind of a gravitational core?
They do. So if you ask what are these globular clusters doing out there, the chief answer is not much. Most of them are arcing high above the galaxy, and that is known as the apogalacticon, its high point in its orbit, as opposed to the close point of its orbit, which is known as the perigalacticon. So when they're out there, they're actually moving very, very slowly. And that was something Drake counted on when he sent his message. He knew that the proper motion of M13 would be trivial over 25,000 years, and the radio signal would still hit the globular. But as they plummet towards the plane of the galaxy, they pick up speed, and they're going fastest when they pass through the galaxy.
You know, I was thinking of that signal that was sent out. And so think of the poor astronomer in one of those globs receiving a signal once and never again.
Yeah.
Wondering, now what do we do?
That concept that Drake sent it to the wrong place because they didn't send it where the globular would be in 25,000 years. You're saying, no, he thought about that, but he decided it wouldn't be an issue.
Yeah, he thought about it. He said there will be enough dispersion of that radio signal that it will still hit M13 where it will be in 25,000 years.
So what's he going to say in 50,000 years when they don't answer? Huh?
Well, I think the bigger question is that, modern astronomy shows that the tidal forces of these stars that are so close together are so strong that planets would be stripped away from their parent stars. And but who am I to question Frank Drake? Or Asimov, for that matter.
What motions are the stars taking within the globular?
I'm sorry, Alex, what was that?
What motions are the stars taking within the globular? Are they bees
Yeah,
whizzing
they're
around
all
the
whizzing
hive, or
around the center of gravity of the globular star cluster. And so again, it's similar to the way the globulars themselves are orbiting the center of the galaxy. So stars out at the periphery are moving quite slowly, and as they move in toward the center of the globular, they whiz through much faster.
So you would expect with the density of those stars that there'd be quite a few collisions over time.
Yeah, unknown. I mean, there's an interesting article in Astronomy, or not Astronomy, Sky and Telescope magazine about star collisions and mergers, and it's a new emerging field. And I would think that globular star clusters would be a ripe area to try to find those.
yeah. So basically, we can't really say that they move in smooth orbits, though, because there'd be so much perturbation between one star and all its neighbors going by.
But they're incredibly tightly bound by gravity. That's what all the models show. It's like it's very, very, I mean, that's why they survive the mergers when the galaxies collide, like Gaia Solidus and the Milky Way. Their gravitational binding is so strong that they really don't get disrupted even with those kinds of tidal forces.
Molly, do you have a question? Is that yours?
Blue
No, I
stragglers?
was just gonna double check on clarifying Alex's question. Also, I managed to grab the stream earlier, so I think Rod, you can start playing your video again, and that should be smoother now.
All right, let's.
I don't know which of us was the Astronomy channel that put this one in, but what causes blue stragglers?
That's a complicated thing. It's basically when stars on the main sequence start to move over to red giants, there's a little bit of a zig that occurs in that curve that's called the knee. And then they move towards red giants, and some of the blue or supergiants in that lag behind in that process, but not all of them. And so those stars are known as the blue stragglers.
You know, you would think there are so many stars there that a couple of them would wink out, you know, collapse and form the black holes. And hey, I saw a star there, and now it's gone.
Not gone. Yeah.
Well, I'm wondering if like the stars, I'm trying to remember if there are examples of massive stars like greater than 8 solar masses that live on the span of 10 billion years, or if they tend to have shorter lives.
No, those are stars that live fast and die young when they're that massive. They just
probably why
fuse.
there's not supernovae then in globular clusters.
Yeah.
So you would think that the proper motion data, you know, might show black holes.
Well, that's how we found the supermassive black hole at the center of our galaxy, was by actually probing stars and seeing them whiz around. But the stars, you know, are much closer to that. And so from our point of view, those stars are more widely separated. In globular star clusters, it's so dense, we just can't see the motions of the stars near the core to pick up the black hole, except with the exception of it's been done in M15 and another globular.
Are they pointing Webb at any of these clusters? Any studies going on? Do you know what?
I've seen one Webb image of a globular, and new studies going on in that, but not many yet. No.
You can go ahead and put your slides back up so we're not looking at the infinity mirror.
Oh my gosh, you're doing that? Okay.
And you're going to process now. So I think you know, this isn't the end.
Yeah,
of the
we're going to go on
presentation.
to processing globular cluster image
Processing.
data. So I think good globular cluster images should contain 4 components. One would be the beehive effect of these faint stars way out in the periphery away from the core of the globular cluster. We want to show that. We want to have resolution in the core, at least as much as possible. We want to bring out details within the cluster if we have examples of some of those things that I discussed in that earlier section. And lastly, as I said, they should be colorful. They shouldn't just be white blotches of spray paint on black velvet. So those are the 4 components that I want to bring out in globular star cluster images. Now, there are lots of ways to process globular cluster data. You can do curves in Photoshop. You can do HDR processing in Photoshop. You can do the screen transfer function moved over to the histogram transformation in PixInsight. You can do HDR multi-scale transform in PixSight. And all these work, but in my experience, every one of them results in a burned out core where you don't see the details in the core of the globular. So my globular processing routine is different, and I want to say out front, I'm neither a Photoshop nor a PixInsight purist. I use whatever works wherever it works. A full disclosure, to do what I'm going to do, you're going to need Maxim DL. But most of us have it, even if we moved on to Nina and things like that. And if not, yeah, I'm sure you have a friend that has Maxim DL, and you can send them a file and say, do this, and send the result back to me. But this is a fast, easy, about 6-step way to produce a globular cluster image. I use this on every image that I published in Astronomy magazine, and I think it produces great results with relatively simple steps. So let's do the demonstration with M13 data. And so I'll drop this, and we're going to go to PixInsight. Can everybody see my PixInsight screen?
Yeah, looks good.
Yes.
Okay, so this is my master stacked image of M13, and I'm just going to give it the radioactive symbol here and stretch it. And as you can see, these are real data because I've got a gradient across it. Looks like I've got an unresolved dust donut here. But what I like about this is that this produces a great beehive effect of these peripheral stars that I want, even though it burns out the core. So basically, I will transfer this screen stretch to the histogram transformation, and then we'll take that and throw it on the image, reset that, and there it is. But we've got a gradient. We can get rid of that here if we want in PixInsight, if you're a peer, so that by just doing a automatic background extraction and setting it for subtraction. So if we throw that on here, there, it's now got the gradient gone. But I'm going to also show you how to get rid of the gradient in Photoshop. So let's take this image, like this one. We'll save it and we'll take it into Photoshop and get rid of the gradient there. So that wasn't the image I wanted.
What?
Nope. 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 Well, I think that's it right there. Yeah, there's the thing. So basically, I'm going to take my lasso image or tool here, and I am going to exclude or include the globular star cluster itself. That didn't come out very well with my mouse. And there's going to be a gradient around that star. So we'll say select inverse. And we'll go to gradient exterminator, and we'll go coarse and high. And now deselect that. And now we'll take the magic wand tool, select things, and now we're going to exclude with the lasso tool. Again, we want to save that. And the star with its glow around it. And say filter, gradient exterminator. This time we'll go fine and high. And now we'll darken this up. So I typically want my background sky to have a value if I move this into RGB mode and put some sample points like there, 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 and there, and pull up levels, I want to get my background sky down to about 25. Right about there. Okay, so I've got a great beehive effect here, but as you can tell, this core is really burned out. So I'm now going to show you another trick that you need maximum DL for. So I'm going to go back to the original image here in maximum DL. And you want to go to Filter and Digital Development. Now, if you look in PixInsight, you'll find Digital Development under Obsolete. And I disagree with that. I teach my surgery residents, not all old techniques are bad and not all new techniques are good. I can't really reproduce what Maxim DL does with the digital development in Maxim DL, but this can work some real magic. So you pull it up and you want to have the settings of FFT at low pass. We want the hardness set to mild, and check auto for the background and mid-level, and then hit OK and wait for the magic to happen. Now that's just spectacular, but it's got a couple problems. One is it's too faint. So if we take this histogram slider and we basically get past all this noise we've got out here and set that height point right about there where the data really are, that's about the right brightness we want. The other things, it's a little too crunchy for me. It's also a little too flat. The whole globular looks about the same brightness, and they really ought to be brighter towards the center. But we can fix that in Photoshop. The real thing we don't like is what it does to all the field stars and the galaxy. It just wrecks other things. So we're going to save this. So I go File, Save As. And we're going to save it as a TIFF, so we can use it in Photoshop. We've got to make it 16-bit, not 8-bit, and go to Manual Stretch. And we want to use the screen stretch, the way we've got it stretched right here. And I'm going to save that as Digital Development and have it in there. So now we'll go back to Photoshop and open that image up. So here that is. And so we're going to hit Select All, Edit, Copy, and go back to where's that image? This image, and hit Edit, Paste, and put it on top. And I'm going to see, are those actually aligned? No, they're not. They should have been. All right, so we just get the Move tool, and we'll just scoot it over where it's supposed to be. Right about there. But again, I hate these stars. So let's put a hide all mask on it. Now we've got the beehive effect that we wanted in the PixInsight screen stretch, and we've got the good stars in the background. So we go get the brush tool, make a fairly good sized brush that will cover the core, put it right over the core, make sure we have a white brush, and hit it once. And we can brighten that up a little bit if we want. Now we've got essentially the best of both worlds. We've got the good stars and we've got the resolution in the core. But here's where I can set the Shapley Sawyer I want. It's like, here's with none of that showing up. And as I said, we want the globular cluster to look a little bit brighter toward the center. So we basically can dial this in until it looks brighter in the center, not quite as crunchy. And I find for a class 5 globular like this, about 85% works great. And so now we've got the best of both of those, and we can flatten the image. Now we're going to go after the details in the globular cluster. So I'm going to make a copy. And this time we're going to use the high-pass filter. The two things that help bring out those details are that digital development and the high-pass filter. So we'll go filter, other, high-pass. And we start out with nothing. And as we slide the radius selector gradually toward the right, we're watching for that propeller to show up. And it seems to show up pretty well at right around 14 or so pixels. So there we go. We'll hit OK. And now we want to put a hide all mask on this. Change the blending mode to overlay. Go back and get our brush tool. And this time we want a small brush. And we want 100% opacity and flow. And we're going to paint in that dark lane of the propeller where it is. And if we want more of that, you can just double the number of high pass layers you want, and you can just basically build it in. But we also need to blur that mask a bit. So I'll go filter, blur, Gaussian blur. So we don't have such a abrupt edge. So that looks about fuzzy enough. Okay, so there is our luminance, and we can flatten that. Now, the other way you could do this in PixInsight is you could make a mask with a hole in the center of it, add in the digital development, and then with Pixel Math, pick how much you wanted, like 100%, 85% like I did, to get the same effect in PixInsight. So now we're going to go to the RGB image, and we're going to stretch that. And so I'm going to just go image, curves, adjust. And I use my standard curve, which looks like that. Darken up the background sky. Do another iteration of that curve. Darken up the sky a bit again. And now we're beginning to see a bit of a gradient. So we'll get rid of that with Gradient Exterminator again. Let's see, I want to do that include. And select the inverse. Gradient Exterminator. Again, coarse and high. Deselect, get the magic wand tool, select the sky background, go back to the lasso tool and go with exclusion. Again, leave this out. And that. And run Gradient Exterminator, this time fine and high. And let's darken up the background a little bit. And then maybe one more gentle stretch. So we'll go image, adjust, curves. And this time I've got what I call a gentle curve, like that. And again, darken up the sky. Something about there. Okay. So now we're going to go get our luminance image. Nope, that's not it. Which one was it? Not that. Not that. That one. Okay, sorry. So we'll say select all, edit, copy, and we're going to put that on top of our RGB image. And now I'm going to make another copy of this so I can manipulate it if I want. And we're going to cover that with the luminosity blending mode. And another thing I like to do is I like to put a mask in with the color. So I'm going to add a mask on the color layer, go into the mask, and I can just put an image in there because I just got one, and we'll turn it into a mask by cranking up the black point to get the sky as black. We don't want a lot of color noise in there, and cranking up the globular. So now we can get color where we want it and not where we don't. Okay. So the next thing we want is I'm going to do a shadow highlights adjustment on the color layer. And if we turn this up, we're increasing some of the color in there. And then we're going to go to lab mode. So change the mode to lab color. Don't merge them. And pull up curves. And we're going to adjust the A channel by putting an inflection point right in the center with 0, 0. And crank up the reds and greens. Something's wrong. There we go. And image adjust curves. Go get the B channel, which controls blues and yellows. Put an inflection point in the 0, 0 here. I didn't do that right. Control M, B channel. 0, 0. And turn up the blues the way we want. And so here we have basically my start of my LRGB image of M13. So as you recall, the final image we looked at it many times. Came out like that. So hopefully that's what we can all do with those techniques. So let's just go back and finish off our presentation after that demonstration. So in summary, globular clusters have tremendous astronomical and cosmological significance. Globular clusters are great astro-imaging targets because they are beautiful, bright, large, and colorful. And I hope that you will become excited about globular clusters and add them to your astrophotography portfolio. And remember, the next time you hear someone say to you, if you've imaged one globular cluster, you have imaged them all, hopefully you can tell them otherwise. And with that, I'll stop sharing.
All right. That's a really fun story of, I love hearing about some of the science history with that, and then getting to see how you process some of those to bring out some of those structures that when you visually look at these things, you can see, but can be hard to bring out in a photograph of them. Yeah, you can hit that stop presenting. It's kind of near the top of the view there. That works too. Cool.
Got it.
Let's see. I don't think we had any more YouTube questions. What
So-
about any folks here in the room?
Molly, do you know who was jumping in on our stream over on YouTube? Not,
Are you talking about the guy talking about the binoculars?
yeah.
I don't know. Whatever.
Okay.
The fly buzzing in the room.
Rod, I like globulars. When I first started this hobby, late 80s or so, I looked at globular clusters till like forever in the 90s as well. I got my first go-to, and I just looked at globular cluster after globular cluster during my outings. It was good.
That's
It was
what I
great.
did
I love
too.
them.
Yeah.
And you're absolutely
here's
right.
that unremarkable globular right there.
And
Are
we
you
can kind of
showing
see
it,
it.
Sherry?
Oh, you can't see that, can you?
It's
Well,
kind of
it's,
fading into the background.
It's coming in and
Uh,
out, yeah.
It's in and out. Okay, yeah. That's in a book that turned up on the doorstep a couple months ago. My
Ah.
image is in it for M54, so
Fabulous.
it was the Sky Atlas.
That's awesome.
So you're certainly right. If you're looking through a telescope, there's really more to see on a glob than there is on a nebula that you basically, aside from, I mean, what,
It's really kind of one of those backward
M16?
things.
I mean, what else can you actually see?
Yeah, it's really kind of one of those backward things where like sort of like the planets a lot of the time too. It's more fulfilling to observe the globulars than to image them sometimes.
I can remember that I got really tired of looking at fuzzballs in a telescope, which is, you look at the galaxy, that's what you see, a little cotton fuzzball.
Yeah.
You don't see anything.
Yeah, it'd be fun to try and image some globular clusters and see if you can kind of pull out some of the same things that are so obvious to the eye, but so difficult to see in the image. So I have to add some of those to my list as well.
Keep it
any other questions?
PG, Arlene.
Huh?
Oh, I'm sorry, my wife just
sorry.
kissed me goodnight, so
Oh,
I said keep it PG.
All right, any other questions from folks in the room? Any parting shots from YouTube? Yeah, I got a couple of fascinating presentation, awesome presentation. Somebody out there still uses Maxim DL.
I said all old stuff is not bad.
Well, if you're using ACP, you're using Maxim.
Yeah.
I guess
Mainly
no
with
choice.
PWI.
Nina. Okay. All right. I think if that about wraps it up. Yeah, don't forget to like and subscribe on this video so that we can reach an even broader audience, get more out there. Apologies again for the stream issues. We haven't practiced doing a stream handoff in a while, and the software has changed a bit since since the last time we practiced. So we'll probably go practice that a little bit to make sure that that works better in the future. Yeah, come back next week to see Craig Stocks talk about ways to speed up some of the tedious parts of your imaging and how to automate some of the processes. And we hope to see you next week. And I guess I'll take us out because I ended up grabbing the stream. So have a good night, everybody.
Rod, you're welcome to stay on if it's
Yes, yeah.
not too late there in Portland.